All right, Kendra, do you have a specific question?
Yeah, I got lots of specific
Someone give me their ruler. I would like
How do you do, can you give me ballparks on like 8 and then can you tell us how to do 8E?
Yes, 8E.
8E and 9.
Oh my gosh.
I got 8E.
Let me tell you.
I got it. Don't worry.
Just.
Should be the same because work is changing. Right? Yeah,
So let's just start at the beginning on problem number 8, right?
okay.
So here's the rocket, right? You have some force applied. Now, let's just play the what if game, okay? Let's say, what if the rocket had a gravitational pull of negative 20 newtons, but the engines could only provide 18 newtons of upward force? Would the rocket engines be capable of doing any work on the rocket itself? No. Why? It's going to exert force. It's going to fire the engines. It's going to look cool. It's not going to go anywhere because the rocket itself won't change its kinetic energy. Okay? So this is a situation, just because you apply the force doesn't mean that you're going to do work. Now, is the work being done within the rocket engines? Yeah. You're taking these gases, you're heating them up, they're exerting forces, all this good stuff. But if you're talking about the rocket itself, no work's going to be done because the force isn't going to exert through a distance. Now, let's say that it can actually exert 22 newtons of force. Now, if you fire a 22 newton rocket engine, will work be done? Yes, but it's only the difference between these two. So the net force that you will use in your calculations is just the 2 newtons. Okay? So that's why I said, I was nice, and I said, look, this is the net force. So that's, you don't have to do anything with it. All you have to do is take that force, multiply it by the distance, that's it. Okay? All you have to do. That's it. Don't make this difficult. So then, that's what you're going to find on A. So what's the change in kinetic energy of the rocket during liftoff? What's the primary purpose of the rocket engines? To change the kinetic energy of the rocket itself. Okay? So you know the work that's done, there's your answer to A. Then you know your answer to B. It's the exact same thing. Okay? Now, when you get to C, what's the final velocity of the rocket? Well, do you know the kinetic energy? Yeah. Kinetic energy equals 1/2 mv squared. If you go with the Rollins equation, you can solve for velocities, which should be something close to your age right now, ish. Okay? Ish. Ish. Now, at this point, and here's what's important on the reading on D. Was the potential energy of the rocket at its maximum height, assuming that the point where the engine is shut off is given a value of 0.
What the heck?
Oh, speaking of rocket engines. So, now, keep in mind, if you visualize this, so here's the rocket. We're going to only fire this engine till about 0.45 meters. We're just testing this engine to make sure it works. We're not putting this thing into orbit. Okay? All we're doing is starting it here. We're going to fire it for 0.45 meters, then we'll shut it off. That's it. So at the end of this time, you have a certain amount of kinetic energy. What we're saying is the point where I shut off the engines, we're going to call that a reference point of 0. So look, you know how much kinetic energy that you have, right? So it's like if I throw this marker up in the air, and let's say this is the rocket, okay? So if I throw it up in the air with 2 joules of kinetic energy at its maximum height, how much potential energy can it have? 2 joules. So whatever kinetic energy it has, when you shut it off, if you call that the reference height, then that's how much potential energy that you're going to have at the top. So you're going to get your answer to A, B, and D are all the same. And your answer to E should be something close to your age again.
Oh, got it.
1/2.
I put diff x equals b.
1/2 b squared over g.
Hold on, but it's going to be a little negative.
Right? And gh.
I'd go MGH.
And then it
On
just solve
4D,
for
did you do?
Oh,
Yeah.
MG8.
Because you already know what your energy is.
Or what? D? Find the distance.
Okay. Did we clarify that?
Yep, we got to move on though in
Are
1
we
second.
assuming that when we're trying to find the,
Mass is 10 kilograms.
no, never mind.
Gravity.
Wait,
times
how do you find
height
the distance
is-
though? How do you do that?
What distance?
What's the height?
How high is the rock? Oh, that's the height, not the distance.
MGH.
Wait, that's kind of the same thing though. Isn't it?
Oh, frick.
So,
Okay. Hunter, look.
is the final
Look.
velocity 0?
So what's the
Yes, but look, you're
UG?
making it difficult. If I give this thing 2
1.75?
joules of energy, kinetic energy here, how much potential energy does it have up
God,
there?
I hate physics.
And 2 joules potential energy equals MGH. Solve for H. Don't make it difficult.
9.
9?
I
Oh,
had the
dear
exact same answer that I
Lord.
got before, so apparently I
Okay,
did it right.
so 9 starts off as a momentum problem.
Oh, that.
Did you not read it?
Words are hard. You look particularly casual today there.
Oh, I know, and they ripped. Chandler stepped on them and they ripped.
Okay.
So what's. Ooh.
Ooh.
You know, if you give me a sewing kit,
Yeah.
I can stitch those up for you.
No, remember
Okay.
I almost sewed your button on like at prom at dinner?
Yeah, but you didn't have.
I didn't have a sewing kit.
So what you should see, and pay attention to this when you answer 9A, Timmy and Susie are going in opposite directions, so therefore their momentums have to have
Equal and
opposite signs. Okay, so just pay attention to that little bit right there. Now, can either one of their kinetic energies on B, stay with me here, can any one of their kinetic energies on B be a negative number?
No.
Why?
That's impossible.
Yes, you can have negative velocity,
What did you
but
get on
squaring
7?
it, so there.
I thought that was such a weird number.
Cool, we got the same thing.
As a, what's a weird number, like 9?
No, on 7, like I got such a really like a tiny number.
Like
Oh,
39.3.
no, 7 is a big number.
Like
I really screwed it up.
Oh, I didn't.
Yeah, how did 7?
How
How did you
big?
carve that?
I got a very small number.
10 to the second?
I don't know how you start that.
Let,
Or 10 to the
let me
10 to the
explain,
39?
let me explain the basis of how I came up with number 7. I was in Australia, in the outback, and they were having like a big agricultural fair.
Are you being like serious?
No, I'm being completely serious.
I can't tell you said that in such a way that
No, summer 1997, Alice Springs.
Okay.
Okay?
Do you have any pictures to corroborate this story?
Okay, I don't know.
Corroborate?
I didn't know you were being
Yes.
serious.
Okay. So they were having a big county, kind of like a state fair. And Australians are horribly independent. They hate wearing seatbelts, but the problem is there's carnage on the road because they tend to hit kangaroos, which completely mess up the car. It's like hitting a deer. So they were trying to convince people to wear seatbelts. So they took this massive crane, and Australians are given to excess. So they figured, okay, well, here's how we can get their attention. So they took this big massive crane and lifted a car, and then they were going to drop the car so that when it hit the ground, it was going the equivalent of about 60 miles per hour, which in this case is like 100 kilometers per hour, which is about how fast people drive in the outback. And they had a crash dummy in there who wasn't wearing a seatbelt. So they wanted to show people, hey, this is what happens if you're in a car crash and you're not wearing a seatbelt. Okay? So that was the basis of the idea. So you're the crane operator. It was like, okay, how high do I have to lift the car so that when it lands, it's traveling at this speed? Okay? So literally, that was the basis of the problem. True story. So here's the deal. So
I'll go back.
here's the crane, here's the car. Now, on all of these problems, when in doubt, make a chart. Okay? So,
39.
what are my two types of energy I could possibly deal with in
That's
this
not a very big
problem?
number.
Kinetic and potential.
Yeah, UG and KT. So when it's up at the top, what's the only thing that you have?
Potential.
UG. So up at the top, I'm going to have some amount of UG. My
Maybe the square
kinetic
root of it.
energy is going to be 0 because it's not
Figure out the
moving.
square root of that.
So this is going to be this, whatever I have here is this. Now, when it hits the ground, how much UG do I have?
know how you're getting 13.
0. So whatever UG I start with at the top is going to equal my
Minus 2.
kinetic energy at the bottom. Because everything still has to add up to the same sum. So you go, oh, okay, well that's kind of cool. My UG is going to be mgh. How can I determine my kinetic energy?
Are you squaring this?
1/2 mv squared. Guess what drops out? The mass. That's why I didn't give you the mass of the car.
I was wondering that.
It was like
It's
like when you worked
9.8.
through it yesterday and you said
4 times 9.8.
okay.
So then H equals.
So your height
Whoa.
should be around 40.
Oh my god, I got that and I just erased all of it.
Around the
I
edge
hate
of the
myself so much.
Wait.
I hate myself so much.
Yes.
What did I do? Oh my god, I'm so mad.
Oh yeah. You said you got a tiny number.
And then I redid it and I got it right. I just didn't square the number on the top, but I did all the work right and I like had it down on my paper right, but I didn't square it. And then when I put it in my calculator, then it was right. And then it was a different.
Hey,
It was a
hey,
different.
be nice
Hey,
to her. Okay?
thank you, Hunter.
Talk to girls like that.
Dang, why is there so much?
Okay. On number 4, your maximum height, because it all hinges off each other, your maximum height should be around 90.
For what number?
4D
Okay, how do you get to that?
ish.
How do you get to that number?
Ish.
How about
On number 3, all of your answers should be something times 10 to the third, except for the velocity.
we have to find velocity?
Yeah, on D.
up.
Yes, we have to find a velocity.
I'm doing so much math.
3D.
At least this assignment we didn't have to like write quotes. We normally got
I literally got the answer and then I
Okay.
erased it. Like, why do I do this? to
Anything
myself?
else? Once,
How do you
twice.
get D on 4? What's the equation that you use?
On which one?
4D?
Set your kinetic energy just like that.
Use that one.
Yeah, because you know how much kinetic energy it has when it leaves, because you know how much work is done. So all of that kinetic energy has to change into potential energy at the top.
You can just cross out the mass, right?
Because the velocity is squared, so she's just moving faster. She's gonna.
Does that make sense? I got it.
Right?
It's the Rollins equation, man.
Plus, wait, what?
Oh shit, no, we're supposed to solve it for the height.
31.3!
I think we need to have a like quick break.
I can't
I
tell
feel like
you
I'm
what
doing
answer
so
is
much
for.
right now, like I don't even.
It's somewhere in there.
That narrows it down.
I'm gonna give it a free point.
Okay, anything else? Going once, going twice, so. All right. So here's the next thing in terms of energy that we need to introduce, and that's energy stored in a spring. So this harkens back to the very first day that you were in this class, the very first lab that you did. We took a spring, we suspended weights from it. We said, oh, here's a 0.5 kilogram mass. And I said, multiply it by 9.8 meters per second squared. And you're like, why? And I said, you're learning eventually, and now you understand.
Momentum.
So, here's the deal. So, if I take this 0.5 kilogram mass and suspend it from the spring,
What's measured in Newton meters?
is work being done on the spring?
Yes.
What?
Because you're applying a force and it's going in.
It's moving a certain distance, right? I'm applying a force through a distance. Now, if I put even more mass on there, I get even more elongation, right? Now, when you guys did this lab the very first day, you put force along here and elongation here. Why? Because of what? Yeah, because force was your independent variable and elongation was dependent upon that. Okay? That's what you did. But now we need to change this up. Because now we need to look at energy stored in the spring. But now we need to switch these axes, and you'll see why here in just a second. So when you're dealing with springs, we're going to change it up, and we're going to put force here. And we're going to put elongation here. So that's the first kind of switch that you need to have. So we're going to change it up. We're going to put force on this axis, elongation on this axis. So let's just say, that I apply, what numbers do I have? Let's say I apply a 20 Newton force, and it stretches 0.20 meters. So we can come in here, at that point, boom, it's linear function. So this is what's known as Hooke's law, which basically says the amount of force that you apply is directly proportional to the elongation in its linear function. Okay? So let's start with this. So remember, this 0.2 meters is not the length of the spring. The 0.2 meters is how far it stretches once I've applied this 20 Newton force. So it is not the length of the spring. It's how far the spring stretches. This is why this graph goes to the 0.00. Because with no force applied, I don't have any elongation. If it was length of spring, it would actually start up here, because if there was no force, I'd already have a certain amount of length. So it's vital that you look at this and go, okay, I'm applying 20 newtons of force, and it stretches 0.2 meters. It's not the length of the spring. It's how far it stretches. Now, with that said, could I find the slope of the line?
Yeah.
Darn right, Skippy. So, assuming that we go through 0, 0, I'm going to take 20 newtons minus 0, divide that by 0.20 meters minus 0, and I get what?
Okay, not quite there yet.
Did you get 100?
100.
Okay. Significant 0 there. Units? Okay, don't make this difficult. Now, is it Newton meters? Or is it newtons per meter? There's a big difference between the two.
Newtons per meter.
It's newtons per meter. Okay? Now, if it was Newton meters, which it's not, if it was Newton meters, the slope would represent
Work.
work. But it's not. It's newtons per meter. So what this represents is that, what this is saying, is that if I want to stretch this spring out to an entire meter long, I'd have to apply 100 newtons to it. Okay? That's what that number means. Now, when you get the slope of this line, this number, measured in newtons per meter, is what we call K, which is what's known as, bless you, the spring constant. Okay, it's on your equation sheet. Lowercase k, spring constant. Now, this isn't the same for every spring. Okay, this isn't like the universal spring constant and every k has a value of 100. Right? No, it changes depending upon the spring. So if I've got like a much lighter spring, if I apply 20 newtons to it, what's going to happen to the elongation?
Longer.
Yeah, so it might flatten that out and make that slope a lot less. If it's a really stiff spring, then I apply 20 newtons of force, I might get a smaller elongation, and that would be a much bigger slope. So when you look at that value of K, that's going to be a reflection of how stiff the spring is. Really, really big number, hey, that's a really, really massive spring. If you have a very small value of K, that means the spring stretches pretty easily. Okay, got this. Beautiful. Now, is this a linear function?
Yes. Yeah.
How do you express any linear function?
A straight line.
Why?
Dude, that's
Y equals?
NX.
I didn't say how you draw it, I said how do you express it?
I express it by drawing a straight line. Yeah, like, I don't know why you guys so. I mean, you're right. I am, I don't know.
You're not wrong.
What's the value of B?
0.
0. Okay? Now, what do we graph on the y-axis? Force.
Force. Y.
So, F is going to equal my slope, which is K.
K.
And my elongation is going to be
D.
X. Okay, how far it stretches. So, if you have a spring, F equals Kx. So here's what this means. The farther that you want to stretch something, what happens to the amount of force that you have to apply? It's bigger and bigger and bigger and bigger and bigger. Okay? So, if this isn't like pushing something. So when you look at something being like push, if I want to push a car, hey, it's the same amount of force. If I want to stop the car, it's the same amount of force. But with springs, this is important. The farther something stretches, the more force that it takes to make it happen. Okay, same thing in a rubber band. If you just apply a little bit of a force to a rubber band, okay, it's just going to stretch a little bit. If you really want to pull it back, you have to exert a lot of force. Got that?
Yep.
Okay, now, I'm going to draw this again. So we've got 20 newtons, 0.20 meters. This, we said F equals, now in this case, I've got 100 newtons per meter times X. Okay, so this is the linear function expressed beyond just a line. Here's the mathematical expression for it. Okay?
Okay.
Now, do the units work out? If I put in 0.2 meters, does it work out?
Yep.
Why, Sam?
Because meters times meters is newton.
Yeah. So if I multiply meters, the meters will cancel out. I get newtons. Boom. There's my value of force. Right? So if I only want to stretch it half as far, what's going to happen to the amount of force?
Decrease.
It's going to be half as much. Because if I only want to stretch it 0.1 meters, that means I'd only need 10 newtons of force. Okay? Because it's a linear function. Good with this. Now, could I find this area?
Sure.
Me. Could I find that area? Or Kareem, maybe. Kareem.
It's Jareem Jabbar.
Oh, Kareem.
Yeah.
Okay.
Eric, say it.
Eric, say it.
Say what?
Say it.
Kareem Abdul-Jabbar.
Kareem Jabbar? I still don't know his name.
Okay. All right.
I never heard of this dude.
So, me, let's go back to this one. Let's deal with something intelligent. Can I find this area?
Yeah.
What would I do?
Apply the y.
Do what?
You just do the formula.
What formula?
F equals that.
No! This is a linear function. describes a line. I want to find this
Find
area.
area.
1/2 base times height divided.
1/2 base times height. Okay, that's kind of punchy. Right?
Ask Mr. Taylor a question.
So I got 1/2. My base is
0.2 meters.
0.2 meters.
10.
And then my height is
20 newtons.
20 newtons. So half of 20 is 10. 10 times 0.2 gets me
2.
what units? Newton meters, otherwise known as
Work.
Joules.
joules,
Way to go.
which is a measure of
Work.
work. So the area on
Circle back.
a force distance graph, and that's basically what this is, represents the work that's done. So this area is going to equal work. Now,
That's still right?
when I stretch it, am I storing potential energy? Yes. So the work that's done is going to equal my change in, in this case, the potential energy of the spring. Now, let's do a little voodoo with some algebra. So we just said that work equals change in us, right? On a spring. We just said that, right? And we said that that work equals my area, which was 1/2 base times height, right? Because it was a linear function expressed with a line. Now, we said the line was F equals kx. True? So now we're going to do some voodoo at this point. The base is measured in what? Meters, because that's how far it stretches. So I'm just going to put in x for that distance. The height is going to be measured in, which is a measure of force. Okay? So basically I take 1/2 x times force. But because this is linear, we said that F equals kx. So can I put kx in for force? I think I can. So now I have x times kx, which becomes
Kx squared.
1/2 kx squared. So
What is going on?
That's too confusing.
So the energy stored in the spring is 1/2 kx squared. Now, hopefully this makes sense. The farther I stretch something, what's going to happen to the potential energy in the spring?
It's gonna
Get larger.
increase quadratically.
Yes, because the x is squared. So if I double the distance that it stretches, the amount of energy stored goes up by a factor of 4. Now, if I double my spring constant, what does that do to my value of us? Yeah, but then if I just double k, I'm just going to double us. Okay? Right? So, yeah, so if you have a really, really stiff spring and you compress it the same distance as you do a lighter spring, you're going to be storing different amounts of energy. Okay? Now, if you're into calculus, I'm just saying.
Not into calculus.
I'm just throwing this out there for those of you that have had calculus or learned anti-derivatives. Okay?
Good.
So for now, we don't, this is.
No, this won't make it.
Slope underneath.
I'm not even gonna.
Yes, so the slope is F equals kx. So here you are between 0 and 2. So if you take the integral between 0 and 0.2 of kx, dx, you get 1/2 kx squared, which gets you that area.
All makes sense now.
So for those of you that have had calculus, this makes sense. If you haven't, bless your soul. Yeah. But it will. So I'm guessing at some point a lot of you will take calculus.
I can do it.
Integrals, which now they call anti-derivatives, why I don't know.
Got this, I'm gonna own it.
It just finds the area underneath the curve and you evaluate it in between 2 points and you can get the exact same
You
answer.
should get his.
Got this idea?
I should count.
We're good. Okay.
Let's do a lab.
Let's get up and move. Can we go melt some pennies?
It's like 80 degrees outside.
Well, I'm supposed to count.
Really?
Yeah, the high is like 79.
I didn't know. All you do is derivative. I didn't know there was AP calculus.
Yeah.
She always talks about it. I don't either. How do we even know that? I think he just taught himself all of this.
I can't read that. You just ask him. What's this?
All right. So let's say I gave you this problem. You have a spring, I'm going to put 0.15 kilograms on it, which isn't much, it's 150 grams. And it stretches 0.046 meters, 4.6 centimeters, about like yay. So this is typically what happens with these springs. So I'm going to add not a whole bunch of mass. It isn't like I hung an elephant from this thing. It's only 15.15 kilograms, and it stretches this far. So what I know is, if I've got all that, then if I add an additional 0.5 kilograms to it, what's going to be the new length of the spring? So where do you have to start?
From the beginning.
At the beginning. Nice job, Kim. Starting halfway through the story, not a good idea.
I'm so tired.
Perhaps start with a chart.
Chart.
Equation. Not even an equation. Graph.
Just the
Graph. Let's just start with a graph.
Oh God. No.
Anything but a graph.
We can start with a graph. So, am I going to plot 0.15 kilograms?
No.
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 What am I going to do? Multiply by?
9.8.
So somebody take 0.15 times 9.8.
That should be
0.15 times 9.8 equals approximately 1.47.
Okay? So 1.47 got me a stretch of 0.046 meters. So I've got 1 point, I'm assuming this is linear. So at this point, what can I find?
area.
I could, but I don't want to.
Okay.
Slope.
Slope. Right? So basically what I'm saying is F equals Kx. Do I know the force? Yeah. Do I know how far it stretches? Yeah. What's the only thing I don't know?
Okay.
Okay. So force divided by x is going to equal k. All I'm finding is the slope of the line because I'm assuming that it starts at 0, 0 because it's Hooke's law. I'm guessing that it's linear. So somebody take one
Approximately 31.9.
Okay.
You knew the answer before you even asked the question. That's crazy.
Psychic.
So approximately 32.0. Or 30.
So
yeah.
let's just go with 32 meters per meter. Okay? Right? Okay? So I got this. Now I know my value of K. So I'm going to add 0.5 kilograms to it. How far is it going to stretch? So here's the question. So you got to visualize what's happening. I had the 0.15 kilograms already on there. And now I'm going to add 0.5 kilograms to it. So I was at 0.15, and now I'm going to add 0.5.
So now it's at 0.65.
So do I use 4.9 or do I use the combined mass?
Thank you.
Kendra?
What did you just ask?
Do I
You
take
add them.
0.5?
At 0.65.
Okay, I'm at 0.65.
And then it's times 9.8, so it's 6.37 newtons.
So 6.37 newtons. So now I'm way up here at 6.37, which is so not at scale. But so I know my elongation has to be more than
0.46
meters. Because I'm not going to put more weight to it, and it's not going to stretch this far.
Yeah.
It's gonna actually.
Well, we know our K.
Yeah, we know our K.
So we can solve for the elongation.
Force divided by K.
How cool is
Wow.
that? So we know that's 32 newtons per meter. So the only thing I don't know is X. So what do you
Never mind.
That's okay.
5.02.
Approximately or like this?
5.02.
Wait. He's on it still. Hold on. I'm on it.
0.20.
0.20.
Meters?
Wait, no. Yeah, that's what I got. 0.200.
Well, two significant digits.
2.
I'm not taking it.
I'm more comfortable with 3.
Yeah,
This only has 2.
yeah, but I want 3.
Well,
But
then
you
look
have
at the
3
force.
up there, so.
But you're limited by the smallest number of
Okay, so
significant
just send a
digits.
0 to it.
Oh, that's right. I thought you said wait.
Sig figs.
Yeah, that's right.
Just go ahead and add 2 zeros.
Where are
once
you
to the
plugging
meter.
this in?
Okay.
No, if you want to, that's fine.
I'm
It's wrong, but
Mine's gonna be 3 sig.
Oh crap.
okay. Cool with this.
Wasn't there a
Got it?
square root?
We're not using that.
Good. Okay.
He said we got equal to us.
Now, we're gonna make it even more complicated.
Doing this again.
That wasn't that complicated.
No, 'cause I'm gonna say, now we're gonna make it more complicated.
No,
Can't we just stick with these?
that's always the plus.
What do you put in? 4 fours?
With the added.
Yeah.
6.37
Yeah.
divided by the same K, the 32.
Yeah.
Are you on a baseball game?
Yeah. Are you not?
Dude, I miss like the first 3 weeks and I was like, anyway, we need to come with
Hey, I'm not coming for like. Are you gonna be bad at the last night? I'm not going. So you. 32. I'm not playing with
Go on 7.
I'm over.
When I played with you guys be like, you like, your level. Dude, I ran up to 7. I ran up to the line.
Yeah.
7 on my station wasn't
You
way.
know what tryout started?
See, I was ranked 30.
Yeah, I
You
was
ranked
37.
That's more than you.
Okay.
I swear, bro.
Like it starts to taste like
Will's cool. Like Will's awesome.
it's like
He's awesome. But yeah, I don't know why he didn't try.
if you compare it to
No, Will was.
Right, is Will not good? Again.
yeah. So it's closer to like
Who's he gonna play over John
it's
or
more
Greg?
like rich.
It's a lot of
No, we'll play with KJ.
But kid is not gonna play over
Because my memory.
It's so good. And apparently you can get it. Well, you can get it. Yeah.
Here, I'll give you 3 significant digits.
Thank you.
Appreciate it.
Jeez.
Okay, now that's
What
just
does a
too
man
loud.
have to do to get
You
3
don't
sig
have to.
figs? Clearly, you gotta beg for some sig figs.
Yeah, can you throw a brother some sig digs? You know?
Some sick dig.
Some sig digs.
Okay.
I'm in it for the 6.
Yo. Spare a brother a sig, you're down on my luck, man.
I just need a fig.
You know, don't care. Marlboro Lights, whatever.
Oh, bird.
Okay.
Camels.
New part 1.
Unfiltered. Okay. I mean, if you're gonna get lung cancer, do it right.
Honestly, bro, you might as well. Nothing
Right
worth
there.
it.
At least enjoy it.
It's definitely.
I think we should make a quote book.
All
You
right.
do so many
Yeah, have
things.
one.
You might as well commit.
Yeah, shooting heroin in
You
your
can
arm.
blow some serious
Right.
with the camel
I don't want you to get lung
Okay.
cancer.
You said something about shooting heroin in your arm? When did you say that?
No, I wrote it down. You were talking about switching units, right? Said your boyfriend might have shoot marks on his arm from heroin, but that doesn't mean he's a nice guy. I wrote that one down.
Which is dipping or smoking?
That means you can't just switch it to what's not.
A decent sized log will cost you like what?
Shut up.
Who buys?
I'm crying. So funny.
Okay, back to our story. So, a box filled with whatever you want it to be filled with.
Grant, I hate you.
That was not me. Why is everything?
Because it's sitting beside your chair.
Alright, so there's 2.5 meters per second, and with the mass of 0.3, with kinetic energy, or, yeah,
Yeah.
3.0
Oh, hold on. I gotta give you another, hold on, we'll be consistent.
Newton meter, yeah. So, what is the car moving?
So here's the
What
setup.
is the car moving?
Car is moving along 2.5 meters per second, has a mass of 0.3 kilograms. It hits a spring with a spring constant of 3.00 times 10 to the third newtons per meter. So this is like with the plunger cart that we did where we pushed it and it hit the wall, okay, and then it compressed the spring and then it pushed back. So this is going along and it's going to hit this spring. So this spring is going to start to compress. Now, as this thing compresses the spring, what happens to the kinetic energy of the cart?
It goes
It goes down. What happens to the stored energy in the spring?
It goes over.
It increases. Okay? So as this is losing kinetic energy, it's being transferred to the spring. Just like if you throw something up in the air, you lose kinetic energy because you're storing potential energy due to gravity. So here's what's going to happen. Car's going to hit the spring, and it's going to compress it 0.0100 meters, 10 centimeters, about like yay. Okay, so not very far. So what I want to know is how fast is the car moving when this spring has been compressed this far? So what can we find right from the get-go?
Let's do a graph.
We could.
X.
Something bigger.
Force.
Something bigger.
What?
What's bigger?
That's only 1 centimeter.
Can you find the
Acceleration.
Kinetic energy.
Actually, yeah,
The work.
we could.
It
Kinetic
is 1
energy.
centimeter.
No, can't
So,
work.
could I find the kinetic energy of the cart?
Yeah.
Yeah.
Pretty easily.
Pretty easily.
You know what? I'll just do it for fun.
Okay? Now, but let's just look big picture. So once I find the kinetic energy, is there any energy at that point stored in the spring? No.
Your chart.
Okay? So it's all kinetic and no us. But as I lose kinetic, I start to store
Potential.
us. Okay? So as the Toby Keith song goes, eventually we're going to talk about us.
I love this bar.
No, no.
I love this.
Let's talk about us. Okay. Okay. So,
Can we do a secret?
could I find the kinetic energy? Yes.
I'm going to see that.
So the kinetic energy is going to be 1/2
MV squared 0.3938. 938.
I'm gonna try to finish your album.
Good guess.
So, I'm going to take 1/2 times 0.3 kilograms times 2.5 meters per second squared.
Even though it was during school.
Squared. What do you get?
I already told you. 0.938.
Yeah, he's right.
0.938?
Joules.
Okay. Now, what's the significance of that number?
That's
That's
the
the
kinetic
sum.
energy.
that's the
It's the
sum
sum.
of the energy.
Yes, that's the maximum amount of energy I can have at any point.
Can't be more than that.
Can't be more than that.
Can't be more.
It can be less than that,
Doing something wrong.
but I can add things up and get to that, but I can't ever go above that mark. So this is the magic number. So what we have at this point, now we can look at a chart. Okay? So at this point, the only thing I have in play is kinetic energy and us, and then the sum. So as it's rolling, right, we have 0.938 joules. Is there any us? No. So the sum of everything has to add up to 0.938 joules. Good with this? Yes. Life's good. Now, I'm going to tell you that the spring is going to compress 0.010 meters. Okay? Not very far. 1 centimeter. So we're going to compress the spring like yay much, not much. So if I know how far the spring is compressed and I know the spring constant, what can I find? No. I could, but I don't want to.
Potential energy.
This is all about energy.
Potential energy.
I can find us, right? Because knowing this distance and the fact that the K was 3.00
Times 10 to the third meter.
times 10 to the third liters per meter, I can find how much energy I've stored in the spring. Now, this, when I find that energy, has to be less than,
0.938.
because if I find this and it's more than that, something's wrong. I've created energy, which would be cool. But, so, then we're going to get us, which is going to be 1/2 my K, 3.00 times 10 to the third, times 0.010 meters, and don't forget to square it.
I thought that was kinetic. Oh, that's why.
Okay, what?
What's this?
What do you get? With 3 significant digits to appease Mr. Garfield. Mr. Oh, I gotta have 3.
Just makes more sense to have.
Zero.
Okay, I'm good with it. I like it.
0.150.
0.150. Okay? So here's the deal. So if this is 0.150 joules, then is my sum still 0.938?
Yeah.
Yes. That's not going to change. That's 0.938. So how can I figure out my kinetic energy?
Subtract that from 19.
Yes. So if I take 0.15 minus 0.938, I get
0.788.
0.7 what?
88.
88 joules.
So where?
So at this point,
Gave it to
I
okay?
gave you the K.
And then?
Yeah.
Okay, thanks.
Thanks.
All right. So at this point, how much we know that the cart has lost some kinetic energy because it went from 0.938 down to 0.788, and that was gained by, okay, but everything still adds up to 0.938. This is the beauty of this chart. It forces you to keep everything organized. How can I use that to find the velocity of the cart?
The Rollins equation.
I can use the Rollins equation, right? Because I know the kinetic energy. True? So if I go with the Rollins equation, velocity is going to be the square root of 2 times my kinetic energy divided by mass, which is going to be 2 times 0.788 joules divided by the mass, 0.3. Yeah. So what'd you get?
Is that a K?
2.29.
2 times 0.788 joules, which is what that kinetic energy is. And then, yeah, don't use the us. You've got to use the kinetic energy. So what'd you get?
2.29.
2.29?
Meters per second.
Now, does that make sense?
Yeah.
Because I was initially traveling at
2.5.
2.5, so I've lost some velocity. Okay? Now, here's the second to the last thing you can do with this problem. As this spring gets more and more and more compressed, what happens to the energy, what happens to my kinetic energy value? It's going to keep going down. eventually will my kinetic energy drop to 0?
Yeah.
Yes, because at that point the spring is
Fully compressed.
fully compressed. So could we find the point of maximum compression?
Sure.
Yeah, because at maximum compression, my kinetic energy goes to
0.
my us goes to
0.99.
0.938. And that 0.938 is going to equal 1/2 k times x squared. So I'm going to know everything but my x. So
I have no idea.
us is going to be equal 1/2 k x squared. So at full compression, I don't have any kinetic energy. So if you go back to your chart, the constant was 0.938 joules. So at full compression, us is going to be 0.938 joules. My kinetic energy is going to be
0.
0. Because this is like when you all push the cart into the wall, and at some point it fully stopped. When it fully stopped, all of the kinetic energy that it had was stored as potential energy in that plunger. And for whatever reason, Mother Nature and potential energy have never got along. I don't know if it was a Facebook thing or what. So nature hates potential energy. So nature goes, I don't like you, and now I'm going to change it back into kinetic energy. Okay. So
why can you use us to find, why is 1/2 kx squared us and kt? Or why not like not kt?
Rephrase your question.
When did we get that?
The equation.
Yeah.
It's on the sheet.
Did we just learn it today?
Yes.
I bet.
Thanks.
New equation.
What is
Do you just get in your own like zone?
Yeah,
All of a sudden it just pops out.
okay.
All these equations
So,
pop
let's
out
see.
of nowhere, right?
What do I need to solve this for x?
Like, wouldn't you just do 2us divided by k?
Yeah, 2us divided by k.
It's essentially just a version of my.
So
So
basically,
it's very similar to the Rollins equation, but instead of dividing by mass, we divide by
Kinetic energy.
k.
Okay.
So, what did she say?
so it's the buddy equation.
Okay. Oh, Lord. Oh,
Lord help us.
joules divided by 3.0. If you get bored in your spare time, work this out. You'll see that it works out to be meters.
It does.
Yeah, it does, I can tell.
I just looked it out.
Just look at it. So what'd you get?
Approximately
0.025.
0.025.
2.5
0.
Look what I did.
meters.
There you go.
Now, does that make sense that that's bigger than that 0.01 that we started with?
Yes.
Yeah, because at 0.01 I still had some kinetic energy.
So that's from the wall that it's at.
Yeah, so what this represents, it isn't the distance from the wall. What that 0.025 represents
Okay, I need
is
to do
that
9.
this is how far we've compressed the spring. It isn't how far it's from the wall. It's how far we've compressed the spring.
Okay. Gotcha.
Does that make sense?
Yeah.
Now, if this came in with more velocity, what would happen to your compression?
It would compress more.
Yeah, because you're going to have more energy in the system. So the faster this goes, the more it compresses. Now, what if we shot that thing back out and then had it roll up a hill?
It's going to come back and hit it again.
Yeah, so if this
Never
was a
ending cycle.
completely frictionless surface,
It's a never
this
ending
would just continuously oscillate back and forth, always compressing it. Now, how
Oscillate.
can you find how high it goes
Okay, well,
up?
we're going to build a better one.
Come on.
2D
Oh,
divided by
yeah,
A.
yeah, this is the real. So how are you going to find out how high it goes up?
Put a meter stick on.
No.
I think that's a good idea.
I like that idea.
That's much easier.
So what's the only thing that we
MGH.
need to add to this chart?
Velocity.
No.
Good.
Alright, V
You're just gonna
squared minus V naught squared.
If I'm gonna
divided
copy
by
all
you
these,
add
give me
some?
credit for it.
Okay.
guess what?
no.
Everything would have to add up to 0.938. So at the top of the hill, how much kinetic energy are you going to have? None. How much else are you going to have? None. It's all going to be
And not Eugene.
yes.
What's Eugene?
And then set attention to
God.
Okay.
You're not supposed to do them on there.
Yeah, but we want
Okay.
to be able to
Now,
do them on.
let me kind of lay out what's happening on number 6. And I don't know why it's a box of purple crayons. When I was typing it up, it seemed like the thing to put in.
The entire box is just purple crayons.
Purple crayon slides along 4 meters per second, hits a spring, boom. How does the kinetic energy change? What's the velocity of the box at that point? How far does the spring fully compress? So number 6 is just like what we just did. Okay? Now, on number 7, we've got Jerry the mouse, as opposed to the purple crayons. You're going to push against the spring with the spring value 408. Compress at 2.105 meters. The spring is released. How fast is he going? Assuming it is a conservative system, which just means that the energy is constant and we're not losing anything to friction. How high does Jerry go up the half pipe? So imagine this. We're going to push him up against the wall, store energy. We're going to let go. He's going to roll for a little bit, and then he's going to go up the half pipe. And when I say, how high is he going to go? Don't answer. I'll measure it with a meter stick. Okay? Just saying. Now, when you get to number 8, okay, with bungee cords. And I'll actually show you the footage of this tomorrow, because this actually came from real data, because in '98 I took a group of kids with me back to Africa, and 2 of them decided to
What?
bungee
Why
jump.
can't we have a field trip to Africa? I think that would be very fun.
Because,
That's a little too expensive and it's not in the budget.
well, no, it's the fact that this Zimbabwe, where this actually
Got attacked
happened,
by elephants.
is incredibly unstable. What?
Finally got attacked by the elephants.
God. Just
Anyway, it's
don't.
horribly unstable, like,
Yeah, politically, it's, the economy is a wreck. It's horrible.
well, maybe we...
So anyway, so here's the setup. So when you bungee jump, why don't you bungee? Why did the sport of bungee chaining never gain popularity?
Chaining?
Yeah, where you instead of a cord, you like tie a chain to your feet. And then
You would just hang.
Well, that might hurt.
yeah, that would hurt, right? Okay. Yeah, so
I
you're
feel like
going to
that would
have
pop
a
your whole
very
leg
rapid
socket.
change in your velocity with the chain. Yeah, bad.
Oh, they would be done.
Okay.
Your ankles would be like.
So basically what happens in bungee jumping is that you have this action going, right? You're falling, okay? Now, as it stretches, what happens to the gravitational pull acting down? As it stretches, what happens to the amount of gravitational pull acting down? Don't make this difficult.
Stays the same.
It stays the same.
All right.
Sure, whatever you say. We'll tell you that we really don't believe it. Okay, now, but as it stretches, what happens to the upward force created by the spring? It's going to get bigger, because F equals Kx. So this thing has a certain spring constant. The bungee cord has a certain spring constant, right? So if you're going to stop, at some point the upward force has to be bigger than the downward force, or you're just going to keep falling. It's bad. So at some point, that upward force has to be greater than the gravitational force acting downward. So let me set the stage. So you're going to fall for 12 meters before the bungee cord even begins to stretch. So you're going to have 12 feet of free fall, okay? Falling 12 feet. Then the cord's going to begin to slow you down. So what you want to do is determine the spring constant of the bungee cord. So here's the deal. You're going to eventually end up 31 meters below where you started. Okay, so you're going to fall for 12. You're going to end up at 31. So how far did the bungee cord actually stretch? You fall for 12, you end up at 31. 19. So the cord is actually going to stretch 19 meters. Now, visualize this. At this point, you are 31 meters below where you started. You're down here. You're 31 meters below where you started. So here's the setup. Leave the spring out of it. How much energy change would there be if you went from 31 meters back up to the top? How could you calculate that? What'd you say, Lexi? Ugh. MGH, right? So the fact that you fell or the fact that you go back up doesn't make any difference. It's still 31 meters times MGH. So the UG that you store here has to equal the US that you're storing in the cord. Okay? Because that's how much energy that you have to store way down here, because that's how much it's stretched. So what you want to do is set US equal to UG to find the spring constant. Now, at the bottom, what are the two forces acting on you at the very bottom? Gravity and the spring, right? True? So when you're down here, okay, you've got gravity pulling you down and you have the force from the spring pulling you up. So which one has to be bigger? Force from the spring. Otherwise, bad things are going to happen. So when you have a difference of two forces, what can you calculate? A net force. And your net force always equals MA.
I said that.
So how can you calculate the force from the cord? F equals KX. Okay, so keep that in mind. All right, you're on your own.